Okay, class, this lesson is going to be 13H, and it's basically applications of laws of sines and cosines. We have basically three major objectives here. First one, can we properly apply law of sines and cosines and knowing which one to use when? Number two, understand a little bit new vocabulary for us, which is vectors, magnitude, direction, you know, different mapping layouts. And this is something you're going to cover in further math classes, but we're going to give you a little bit taste now and kind of see how well you apply it. And second is, or the third one I should say, is I'm going to show you several different systems that use this and how they're different, and you have to adjust your problem and your understanding of the setup based on the context of the question. So this is different mapping layouts, different types of travel, and they all use different systems. I use a lot of this in my engineering that I do and architecture. Pilots use it for flying, and again for navigating ships at sea and so forth. So let's go ahead and take a look at first two different ways to show location. Okay, now we're very used to ordered pairs. And what is simply an ordered pair? Let's go ahead and graph something here of the context 5 comma 5. So what's that mean to us? That means we start the origin and we go over 5 spaces and 2, 4, 5. We go up 5 more here, and there's our dot 5 comma 5. Okay. Now if we were to draw in the triangle that we've been doing, like for trig and figured out the different relationships, we could draw in a horizontal line here or a vertical line there. That's 5. That's 5. And then we'd say, okay, let's draw in our terminal side here and draw a line such like this. We would have ourselves a reference angle, and this would be our hypotenuse. So I'll just call it H. But again, how do we show this location? We'd show it as 5 comma 5. Okay. Now I'm going to show the exact same thing. I'm simply going to copy this blue line over, and I'm just going to put it right there. Now instead of showing an ordered pair, how do we show the location of this point up here? Well, we can simply give it magnitude and direction, which is down here. Now again, there's a lot of different ways of notation of doing this. I've seen a lot of different ways. The way I use it within the CAD software that I use is I use the brackets in the end here, which tells the computer that I'm typing in a magnitude. Now what's magnitude? Magnitude is size or distance, okay, and that's the first value. Then the second value is direction, and that is given as a degree measure of rotation. Okay. Now again, the software that I use, everything starts at 0 being on the right-hand side, similar to that of the unit circle. So, and here I'd say, okay, how long is this line? Well, being that it's over 5 and up 5, our hypotenuse is 5 radical 2. So 5 radical 2 is the magnitude. And again, what's the rotation? We start at 0 and we rotate it up 45 degrees. Okay. So in the computer, in the CAD software, I would type in 5 radical 2, comma, 45 degrees. Okay. And again, it's just a different notation of showing location. And we're going to use this principle in different systems that use mapping and location and travel and on this. And then we're going to use that system to then apply law of sines and cosines. So there's a lot of work involved here, but we're going to see how we do. So let's go ahead and take a look at the different types of systems that use magnitude and direction. Okay, now we're very familiar with the unit circle, and we always have a starting point of 0 over on the right-hand side. Positive rotation goes counterclockwise. Clockwise rotation is negative. Okay, now let's talk about this word bearing. Bearing is something that we use in a lot of mapping skills. Again, guiding boats on the seas and so forth, use bearing as well. And what bearing is it uses the compass, and it starts with a north or south heading. So I'm going to give you a notation of something that looks like this. North 30 degrees east. Okay. And what that means is you're rotating 30 degrees to the east from the north location. So from here, what it means is I'm going to start at the north location, and then I'm going to rotate 30 degrees to the east. So notice the east is to the right, and then that's where I put my terminal side. Okay. So again, I guess I should have done it in red there. I'll do the next one in blue. Let me do another example here. So let's see if I did south 60 degrees to the east as well. Okay, so here I'm going to go to the south now, and then I'm going to rotate 60 degrees going to the east, and we have a location that's over here now. So that's just showing a different rotation. Or let me do one more. If I said, okay, south 10 degrees to the west. So, and again, I'm going to go south again, but this time I'm going to rotate to the west, to the left, 10 degrees. So again, that's how you show bearing. And how do we recognize that? By this notation is very popular in that regards. Okay. Now another system that again uses um, direction and magnitude is headings. And a lot of times airlines and pilots use this, for navigating the skies. So the way this works is it works off of true north, which is 0. So it's a lot like the unit circle, but instead of 0 being on the right-hand side, 0 is due north. And now positive rotation, instead of going counterclockwise, is clockwise. Okay. So 90 degrees is to the right, go more clockwise, and your 180, which is due south, due west is 270. Okay, and typically for pilots, you always give a heading in a positive number. That way, if you're talking over intercoms, is it positive, negative? You couldn't hear. Everything's given as a positive rotation, and 0 is due north. Okay, so if I say, okay, I'm at a heading of a 150-degree heading, you'd say, okay, I rotate 150 degrees, and there's your direction that you're traveling, and say you're flying an airplane this way. So again, we can kind of see a vector, the length or the speed of your travel, and then the rotation direction of your flight. Okay, so we're going to use these three different systems. I'm going to go through two problems and showing how we use log, sines, and cosines, and using two of these three systems. We've already very familiar with the unit circle, so let's work on bearings and headings and see the difference there. All right, for the first problem here is, you can go through and read through the problem, but it's basically illustrating this. We have ourselves a legal radio station, and we have two monitoring stations, A and B. Station B is 40 miles east of Station A, so that's obviously a key context point, so I'm going to highlight that. And Station A measures the illegal radio station coming from a direction of north 48 degrees east. Okay, so that is for Station A. So I'm just going to label that so I know what then that is. And then the next one, Station B, measures the illegal source coming from north 34 degrees west. Okay, how far is the illegal radio station from the two stations A and B? So the first thing I want to do is draw a picture of this location. So what we're going to do is let's grab these crosshairs. Now I like to use crosshairs when I do all these drawings because it gives me a little compass so I can get my bearings straight, no pun intended, of what direction I'm looking at. So let's call this Station A. And it says Station B is to the east, so I'm going to grab another crosshair and put it to the east, which is over here. Make a little bit bigger drawing here. And we'll call that Station B. Now let's call the illegal radio station point C. So let's go ahead and draw this in. So the first thing I'm going to do is draw a line in between those two locations, and it says that this is 40 miles. Now the next thing it says is, let's do Station A right here. North 48 degrees east. So do this in a different color. I'm going to go north, and I'm going to rotate 48 degrees to the east. So notice that's how it's going to look. Now let's go ahead and let's do that one in green. Should have changed it there. And let's do the next one. Let's do this one in red. Okay, so I'll do Station B in red. So what we're going to do is start at B, and we're going to go north once again, but this time I'm going to rotate 34 degrees to the west, and we're going to have a direction that looks like this. Okay. And we have a dot there. I'm going to extend this line a little further, and we'll call this illegal station C. Okay. Now, knowing what I know about geometry, the nice thing about the crosshairs and the compass is that we can go ahead and fill in complementary angles. If this is 48 degrees, then this is going to be 42. Again, when you draw these drawings, you want to draw it to some sort of scale and proportion so your drawing is fairly accurate to what you're trying to represent. It really helps you out in more complex problems. If this is 34 degrees, then we're going to rotate down and call this 56 degrees. Since we have ourselves a triangle, we can add them up to 180, find a missing angle, and this is going to be 82 degrees as well. Okay, so now we have three angles filled in. So we're going to now look, okay, if we want to figure out how far it is from station A to the legal station, from station B to the legal station, these here are simply little b and little a, just for location. And again, across here is little c. So what's given to us right now? We have ourselves law of sines, Dr. Evil and Mini-Me right here. Okay, so there's our matching pair. So let's go ahead and set this up. We're going to say, okay, sine of 82 divided by 40 is equivalent to what? Okay, so let's go ahead and do the green over here, green side, B. So we're going to say sine of 56 divided by little b. Or we could set it equal to, do it in red now, side A, which is then sine 42 divided by little a. Now again, I always want to go back to the original setup because that's what's given. That way I'm most accurate. Again, if you ever have to keep a value, don't ever round within a problem. Always store it in your calculator. Get as maximum number of digits stored as possible. Again, I'm going to have you round everything to 4 decimal places in a lot of our problems just to show accuracy of our tools, the calculator. So after going through the calculations, we've gone through this already in class. I'm going to come up with, B, which is the distance from station A to C, as being, let's see here, 33 miles, 0.4874. Again, I'm rounding 4 decimal places. Again, a lot more stored in the calculator. And then for A, change pens here, A ends up being 27.0283 miles as well. So notice here, A should be smaller than B because the angle 42 is smaller than 56. Do that just to check, make sure you didn't mess up somewhere in your calculator, okay? So again, losing law of sines, we use a different type of system of location and distance, magnitude here. Let's take a look at another example here. This one has to do with airplanes. So notice a different system here. Let's kind of read through the problem. 2 airplanes leave airport on 2 different runways, but obviously the same airport. So it's the same location they're taking off from. One flies at a heading of 294 degrees at 325 miles per hour. And so again, notice the heading, and we're going to call that airplane A. And the other airplane flies at a heading of 206 degrees at 300 miles an hour. We'll call him airplane B. How far apart are airplanes after 2 hours? Now that's key right there, 2 hours, because what's that tell us? That tells us the magnitude, the distance traveled, the size of the vector of each airplane. So first thing I'm going to do is start with a crosshair. I'm going to say, okay, here's the airport. First airplane, let's do it in red, airplane A, flies at 294 degrees. So 294 degrees is almost full rotation, definitely 3/4 of the way around. And so it has a direction that looks like that. And that's the vector magnitude. Now, how long has that airplane traveled? Well, it's in the air for 2 hours at 325 miles. So it has traveled 650 miles. That is the magnitude of this vector. Okay, now if this was 294-degree rotation, then we could say, okay, how much is left? Well, we just simply subtract that from 360, and we get ourselves 66 degrees. So I'm going to fill that in as a reference angle back to due north. Okay, so how big is that angle there? Now let's draw in airport B. 206-degree rotation, so again, start here, go to 180 and just 26 degrees more. Okay, so let's go ahead and draw this in as well. I'm just going to take that out because we don't need it anymore, and instead I'm going to put in 26 degrees because that's how far I passed 180 degrees. All right, the nice thing about this is now, how can I use this to help figure out the information? Let's go ahead and put this in. 300 miles per hour, so this is going to be 600 miles after 2 hours. So let's go ahead and put that information on there. I always like to put as much information on the drawing as possible. So again, if this is 66 degrees and this is 26 degrees, and together this has to be 180 degrees, then what's the missing angle? Simply subtract it from 180, the addition of those two angles, and we get ourselves 88 degrees. Okay. Now the question's asked, how far apart are these two airplanes after 2 hours? Well, that's the distance of that line right there. So notice as I'm asking like, the direction or anything of the planes in that regards, but just asking distance between the two. So we're going to use either law signs or cosines. Now notice, let's call this, let's get some points on here. I always like to label my points so I get organized my information. Let's call that airplane A, so, and this is airplane B, and let's call the location of the airport location C. So as we have little c here, little b here, and little a here, okay? So again, I'm going to use law of cosines because notice I don't have a matching pair anywhere. So I have to use law of cosines. So let's go ahead and write this out. I need to solve for c, so I'm going to say c squared. I'm going to derive my formula. Again, not trying to memorize it. If this is my c squared, we know what has to follow. So we have a squared, b squared, minus 2ac. Let's make that a minus sign. Or 2ab, I'm sorry, and then a cosine c. And then from here, we simply just fill in the missing data, and we say, okay, what's A? 600 squared. What's B? 650 squared. Minus 2 times 600 times 650 times cosine. And again, what do we have here? 88 degrees. Okay. Okay, the nice thing about it is, we can just type this into the calculator as one big location. Again, uh, don't round or anything in the problem. If you have to store something, always store it as a variable. And let's see what we get here. C, the distance between these two airplanes, actually ends up being 869.0675 miles. Again, I'm just asking you for 4 decimal places this to make sure that we are using our calculators in the proper way. So that's how we do these two problems here. Again, what we're going to do is we're going to spend a couple days in class doing a little bit more challenging problems, but I wanted to use this lecture to illustrate the different systems, how can we apply them to laws, sines, and cosines, and a little bit of introduction to how vectors work. We're going to have another video to follow talking a little bit more about vectors, again, just to give us a concept and see how can we use our knowledge of laws, sines, and cosines to set up a problem that we can solve.